Dear participants, I will give you information about hazardous arsenic removal from pyrite ash using central composite design. The aim of this study is to remove arsenite with pyrite ash using response surface methodology. The central composite design was used for the optimization of this process. The effects of pH, dosage, and initial arsenite concentration on arsenic adsorption were studied. Arsenic removal efficiency ranges from 72% to 95%. The results of this study showed that toxic arsenite can be removed with pyrite ash. The regression equations and analysis of variance were obtained using the Minitab program. This model is obtained by analysis of variance at 0.92 confidence level. What is arsenic? Arsenic was classified by the World Health Organization as the most toxic element with its carcinogenic effect, and the maximum arsenic level in drinking water was determined as 10 micrograms per liter. Arsenic is found in some oxidation states in the environment. It is usually found in waters as arsenite or arsenate. Arsenate in surface waters under oxidized conditions, under reduced conditions. Arsenite species predominate in groundwater. % of the arsenic in deep well waters is arsenite, which is the most toxic arsenic type. On the other hand, 80% of the arsenic in surface waters such as dams and streams is in the form of less toxic arsenate. The toxic effect of arsenic depends on its chemical form and duration. Arsenite is more toxic than arsenate. Arsenic pollution. Bangladesh, India, China, Taiwan, Argentina, Chile, Mexico, Hungary, Romania, Turkey and many more countries. Pyrite ash is a waste generated during the roasting of pyrite ores in the production of sulfuric acid. At ETI mining facilities in Bandarma, where PA is produced, it is often stored or dumped into the sea and is, therefore, a potential source of pollution. Another possible application is to use it to remove arsenic from the waters. One of the most serious natural pollutants in groundwater is arsenic. There are no previous studies of hazardous arsenite removal using PA. Experimental design. Response surface method. In recent years, experimental design methods have been used widely in many different areas. A classical experiment is an approach that takes time and the number of experiments is high. With this approach, problems may arise in systems with multivariate and with more than one dependent variable. In this case, experimental models and statistical analysis methods play an important role. Optimization of ambient conditions. It provides great advantages in terms of increasing efficiency and reducing costs. The process is easy to control with the effective use of these methods. RSM is one of these methods. Response surface method. The most commonly used design types in determining the RSM functions are full factorial design, partial factorial design, and central composite design. CCD is one of the most frequently used applications. In the CCD method, there are two factorial points, axial points, and center points. The two factorial points of the method consist of the highest or lowest levels of a factor. You can look at Table 1. Material and methods. Material characterization. In this study, the ETI mining facilities, Bandırma, Turkey, obtained pyrite ash were used. The XRD pattern shows the presence of mainly hematite and magnetite and traces of quartz. You can look at Figure 1. Experimental procedure. In arsenic removal from pyrite ash, pH, adsorbent dosage, and initial concentration of arsenite effect were examined at 5 levels. All experiments were performed at pH 8.5. 18 grams per liter adsorbent dosage, 275 micrograms per liter arsenite concentration, 400 revolutions per minute speed and 5 hours. The samples were taken for analysis after adsorption were centrifuged. The arsenic concentrations were then analyzed in an inductively coupled plasma mass spectrometer. Results and discussion. Surface response analysis and discussion. The experimental design was designed with the Minitab program using a 3-factor full factorial CCD. The designed experimental conditions and experimental and predictive values of arsenic adsorption are shown in Table 1. Table 1 shows 8 cube points, 6 axial points, and 6 center points. According to the p-value less than 0.05, the model is significant. The response surface regression results gave the coefficient for all terms, and each effect was independently estimated. You can look at Table 1. When Table 1 is examined, it is seen that the arsenic removal efficiency ranges from 72% to 95%. P-value was used to check the significance of each factor and factor interaction. According to the p-value less than 0.05, the model is significant. The response surface regression results gave the coefficient for all terms, and each effect was independently estimated. You can look at Table 2. The optimum leaching conditions and possible response values obtained as a result of the experimental study are shown in Table 3. The optimum arsenite removal efficiency was found to be 95.12% for 3 experimental conditions. This value matches the estimated arsenite removal efficiency. Optimum conditions were achieved at pH 8.5 when the initial arsenite concentration was 275 micrograms per liter and the adsorbent dosage was 18 grams per liter. The arsenic removal efficiency obtained can be seen in Figure 2 to 4 with 3-dimensional graphics. As seen in Figure 2, the arsenite adsorption was only weakly dependent on the initial pH at pH 12. Arsenite removal increased with the amount of Pa, due to the additionally available adsorbent surface. After a contact time of 5 hours, arsenite removal was 72% at a Pa dosage of 1 gram per liter, compared with 95% at 18 grams per liter Pa. In subsequent studies, the adsorbent dosage was set at 18 grams per liter. The pH effect is less effective on arsenite removal compared to the dosage effect. According to figures 3 and 4, the concentration of arsenite remaining in the solution did not change at the initial concentrations of 50, 130 micrograms per liter in 5 hours with Pa. At these initial concentrations, the concentration of arsenite was reduced below the limit value set by the WHO. Conclusions. In an adsorption study with more than one variable, by using the response surface method, a large number of results can be obtained with a small number of experimental studies. In addition, the results can be analyzed statistically and the results can be made healthier with the obtained graphics. The effects of pH, dosage, and initial arsenite concentration on arsenic adsorption were studied. The model equation obtained using the response surface method fits well with the experimental data with a correlation coefficient of 0.92. Arsenic removal efficiency ranges from 72% to 95%. Optimum conditions were achieved at pH 8.5 when the initial arsenite concentration was 275 micrograms per liter and the adsorbent dosage was 18 grams per liter. The result of the experiment made at optimum points. The optimum arsenite removal efficiency was found to be 0.95. Thank you for listening to my presentation.